welcome everyone to my talk today. And today, I'm going to get you all really excited about the field of gold nanorod biosensing. But I know you're all new to this field. So firstly, I'm going to give you a little bit of motivation about why I think this is all so important. Well, we know how bad it feels to be sick. You're in a doctor's office, and all you want to do is feel better. But to do that, first the doctor comes at you with a really big needle to take a blood test. And what's even worse is you have to wait ages anxiously for that blood test to come back. Well, what we try and do in my research is to get rid of the need for these doctor visits. And instead, we invent a smart biosensor. So this is the final aim of our group, that we can invent this biosensor. This biosensor can be integrated down into the body. And so instead of these doctor visits, you can be at home monitoring your disease on your smartwatch like this. No more doctor visits. How great would this be? And the best thing about this is there are already some of these sensors available. For say, for instance, diabetes, which you see on the top, that's a diabetes monitor. We have here a monitor of your heart rate, or another monitor for monitoring the body's electric fields. So yeah, really good. There's a little bit of a problem, however, that while we can make biosensors for some of these very common diseases, things like, say, infection, there's no biosensor for it. Similarly, heart failure as well. We don't have a biosensor that can really monitor that. So that's what we need to improve. But what we do in our research is we thought maybe we can improve these biosensors by integrating plasmonic gold nanorods into that biosensor. So we take our normal biosensor and we integrate this nanorod into our biosensor to make it more sensitive. And then hopefully, with this more sensitive biosensor, we can both control infection, so stop these infections, and we can also improve outcomes for our heart failure patients. So why are gold nanorods so important? How do they do the magic that they do? Well, you can see here on the left figure, this is a gold nanorod, and it's being excited by an electric field across the gold nanorod. This leads to very intense electric fields on the side of this nanorod. And if we actually look on the right-hand side, my left-hand side, if we actually look at this figure here, we can see this is the scattering and absorption. So on the y-axis is the amount the nanorod scatters and absorbs, and on the x-axis is the wavelength, or the colour that it's absorbing. And you see we can excite. If we excite the nanorod right at the peak, we end up with these strong fields. This gets interesting when we introduce a single biomolecule into this mix. So say we've taken a patient sample, say a patient can be wearing something on their watch or they're hooked up to a machine, and then this biomolecule is floating around in the blood. This gets interesting when this biomolecule then diffuses, we shrink it down, it attaches to the end of our nanorod like that, and then the colour of our nanorod, it's shifted. And so we can monitor this shift in the colour of the nanorod, and we can use this to detect our biomarkers. So yeah, it's really great. But we have some problems. These nanorods, they're just not so sensitive to these really small biomarkers. Yeah, so what are we going to do? We can't, I've told you that we want to detect the biomarkers for these, say, infection and heart disease, but we really can't. So there's some things we can improve. There's some things we just don't know yet. There's some mysteries. Firstly, we don't know how many receptors are coating the surface. So this receptor, it exists at a point where the molecule can come in, attach, and detach from our nanorod. So if we can know how many receptors on there, and we can also know the rate at which these molecules bind, then we can improve our biosensors. And hopefully, we can improve our biosensors and get some real new insights to make these better biosensors. So one way we can do this is using the super resolution technique. We have our gold nanorod, it's coated in these receptors. What we then do is we introduce a fluorescent molecule, it comes in and it binds, and while it's bound, it produces a lot of light from the nanorod. And we end up with this point spread function, what we see on our microscope. We use the super resolution technique to locate exactly where the dead center of that spot is. And so you can see here, on the figure on the left-hand side, it's where that dot is. That's the direct center. This fluorescent molecule, after some time, detaches. The thing we see on our microscope goes away, but we can build this up with many of these events. We can see our nanorod and localize where these receptors were on the surface. This is so great. Potentially it's a good technique that could work. But this has been done already, and people have found it doesn't exactly work like how we'd hoped. Instead of really being able to see a nanorod, say this figure here, the white, black and white figure, is an SEM, electron microscopy picture of our nanorod. And the red dots are where these people have localized where the dye has bound to the surface. But instead of reconstructing the shape of the nanorod, they're seeing a bit of blur. And so we can't work out how this binding kinetics is distributed around the nanorod. And this blur is basically due to the binding times are very short. And because the binding times are very short, there's a low number of photons. We don't get too many photons, and so we can't very precisely locate where it is. So it gets up to being a blurred out image. And so what's even worse, while we can't even find the binding kinetics on the surface here, we can't even really struggle to get length and width. So we can't even see the nanorod dimensions, let alone its kinetics across the surface. So yeah, we have a bit of a problem. I've told you that we really want to map out this the nanoparticle surface, get kinetics to make a better biosensor. But current techniques just aren't sensitive enough to do it. But then we thought, why not, instead of just sticking it to the surface, why not use DNA? If instead we use DNA molecules, we can actually really strongly control the interaction. Maybe the secret to solving our research is the secret of life itself, DNA. And so how do we do this? We take our gold nanorod and we coat it with single strands of DNA. We then introduce a second strand of DNA with a fluorescent molecule attached to it. We let this fluorescent molecule come in, binds to our nanorod. Similar to what we saw before, it produces fluorescence. And then we see this spot on our microscope. We locate the center of that spot, directly where it's bound, and then after some time it diffuses away. We repeat this many, many times, and we end up being able to create this cloud of points. And from this cloud, we can reconstruct our nanorod. And so from here, hopefully we can actually start to extract that length and width. And once we've got a good measure of length and width, then we can get to the kinetics, the number of receptors, and the kinetics across the surface. And with this information, then maybe we can get to constructing our perfect biosensor. And so how do we do this experimentally? We have our nanorods, we've functionalized them with DNA, we deposit them into a flow cell, and then we flow in an imager strand. This imager strand, which is fluorescent, binds to the surface. We zoom in on the nanoparticles, we can see, as you see on this middle figure, the nanoparticles are evenly coated with DNA across the surface of the nanoparticles. And then zooming in even further, we can actually see the surface chemistry on the surface. So we have, this is the DNA docking site you can see here. This is the imager strand, and then this DNA to these 10 nucleotides can bind and unbind. And this gives us our on-off behavior, so we can see each one of these spots. And so this is how experimentally it looks like. Every one of these spikes here, this is a single DNA molecule with a fluorescent molecule coming in, binding to a nanorod, unbinding. And each one of these events is a single spike you can see here. Now, if we actually come to this event, you can see denoted by the star here, and we see that one event, we merge all the photons together from that one event, we end up creating a point spread function like this. This is the image of that dye emission there. And then we can super localize the center of that emission. We fit a Gaussian profile to it, find the exact center, and then that gives us the red dot in the middle there. And then how does this look experimentally? So now you can see every one of these red dots, we repeat this many, many times, and we build up all of these red dots here. And then this blue outline you can see here, this is an algorithm we fit to the shape. So you can see we can start to see a nanorod. But then underneath, this is the actual real nanorod shape we've used found from our AFM. So we use an AFM which profiles the shape of the nanorod, and we can see it actually matches up pretty well. between the shape we reconstruct and our underlying nanorod shape. Yeah, so we thought that's pretty good. But then we're not just happy with one nanorod, we want to see many. Because you don't want one data point, you need statistics to make a point. So that's what we did. We took the statistics, our length and width, from TM, which is the perfect image of these nanorods. We know how they should look in length and width. And then we took the statistics of all of the nanoparticles we fitted, their length and width. So how does this look? Oh, we found it pretty good. So you can see here there are two histograms. On the right-hand side, it's the length, while on the other side, it's the width. And you can see the yellow bars here, that refers to the statistics of the TEM imagery, and then the blue is from our fitted data. And so you can see from the close agreement between our length and width, we can really start to say, yeah, our technique actually can reconstruct this nanorod geometry. So at the start of my talk, we were in the problem. Not only could we not see the kinetics across the surface, or the number of receptors, both which we really need to design our more sensitive biosensors, but we couldn't even get length and width. So we didn't even know how big our nanorods were, let alone how many receptors were on the surface. But I hope through the course of this research, this presentation, I've shown you that, yeah, actually we can get length and width. And with some further research that we're working on now, that maybe we can really resolve this K on and the number of receptors on the surface, design our perfect biosensor, and so we can really start to have a biosensor that can work for infection and heart disease, among others. And so we can see in the future that I'm pretty sure you'll start to see these biosensors that have these nanorods integrated into them. And yeah, we look forward to sharing that with you in the future.
Wow.
Thank you.
Very nice, Adam.
Thank you.
Very nice.
Yeah.
You want to ask questions?
Yeah, questions. Questions come
Or
out.
are we still very busy?